Welcome to CS 650 class AI, Artificial Intelligence. This is lecture number 1 at Morrow College. So let's start with what we will cover in this course. So in this course, we will cover the modeling, inference, learning paradigm. Again, modeling, inference, and learning paradigm, which will help us to solve complex real-world problems. Now, within this paradigm, we will solve the different types of methods that we will encounter in this course. Now, AI is about solving problems, again, using algorithms or technology to solve problems. Example, we have here a self-driving car, virtual assistants, or medical office where we may do image processing such as X-ray. So self-driving cars have to sense the complex scene in front of them and also make a safe decision that again advance the car towards the destination. With virtual assistance, the system have to understand the rich subtleties of natural language. Also, it has to be able to infer the user intent and generate appropriate responses. At the end of the day, again, we need to write some code or build a system. But again, there is a huge chasm between the problem and the solution. But again, we don't want to just start jumping and writing code without a clear plan of action, designing the algorithms, and etc. So again, the first pillar is modeling. Modeling takes a real-world problems and package them into a formal mathematical entity or object, which we are going to call the models, which also can subject to analysis, detail analysis, and can be operated on by computers. However, modeling is very loosened. Not all of the richness or all of the attributes of the problem or the real world can be captured. And therefore, there's a heart of modeling. What do we keep? And also, what do we ignore in the modeling? So an exception to this would be a game such as a chess or Go, where the real world is identical to the modeling. Again, we might formulate the driving problem as a route finding problem, as a graph where the nodes will represent points in the city, the edges between two nodes will represent the roads, and also the cost of an edge represent the traffic on that road or the distance from one city to another. So if we do this design, all the complexity of perceptions are ignored. So again, it's worth noting that losing modeling can lead to errors in AI system, which also can have an adverse impact on people. So a major part of developing responsible AI is to understand and also to mitigate this impact. Now, the second pillar we are going to discuss will be the inference. So inference. Now, given a model, the task of inference is to answer questions with respect to the model. For example, given the model of the city, one could ask questions such as, what is the shortest path? So the focus of inference is usually based on efficient algorithms that can answer these questions. And for some models, computation complexity can be concerned, such as, again, chess, and usually approximations are needed. So one thing we should know is that learning is another major topic in AI. So here we can say that again, where does model come from? We should remember that the real world is rich. So if a model is to be faithful, the model has to be rich as well. But we can't possibly write down such a rich model manually. The idea behind machine learning is to instead get it from data. So instead of, again, designing an algorithm or solving a problem directly, we are going to use the data to, again, construct a model. So again, instead of constructing a model, one construct a skeleton of model, more precisely a model family, which is a model without parameters. And then if we have the appropriate data, we can run a machine learning algorithm to tune the parameters of the model. Now, to summarize, modeling simplifies the real world. Also, we can say that inference answers questions against the model, and also the learning will construct the model from data. So we should know that each step could be challenging to perform and required approximation. So there will likely be a trade-off too. Now, supporting all of this model is machine learning, which has been arguable the most crucial ingredient powering recent success in AI. From a practical perspective, machine learning allows us to shift the complexity of the model from code to data. So instead of writing a lot of code to describe the model, we instead write a very simple model family, such as a support vector machine, neural network architecture, and focus on collecting data to train a model within that family. In this case, within the neural networking or any type of machine learning algorithm. So we can say that the main conceptually magical part of learning is that if done properly, the trained model will be able to produce a good prediction beyond the set of training examples. So again, this leap of faith is called generalization, and is explicitly or implicitly at the heart of any machine learning algorithm. This can be, again, formalized using tools from probability and statistical learning theory. And normally machine learning is break into three parts. We have supervised, unsupervised learning, and reinforcement learning. Again, we are going to cover these topics in our future lectures. So first we talk about the reference-based models. A reference-based model simply perform a fixed sequence of computation on a given input. So example will include most models found in machine learning, from simple linear classifiers to deep neural network systems. Now, the main characteristics of a reference-based model is that their computation are feed forward. So we can see the diagram feed forward, and one doesn't backtrack and consider alternative computation. So inference is straightforward in this model because it is just running the phase computation, which makes this model appealing. Now, refresh model are too simple for tasks. They are very simple for tasks that require more forethought. Example, playing a chess or planning a big trip. So we may have a state-based model overcomes this limitation. Now, the key idea is at high level to model a state of the world and transitions between states which are triggered by actions. Concretely, one can think of state as nodes in a graph and transitions as edges. This reduction is useful because we understand graphs well, and we have a lot of efficient algorithm for operating on graphs. Now, we will consider three types of state-based model. The first is the search problems. So search problems also have models where you are operating in an environment that has no uncertainty. However, many realistic settings, there are other forces at play. Also, Markov decision process, which again handles solution where there's a randomness. Example would be the blackjack. Then we're also going to discuss about adversary games. As the name suggests, it handles tasks where there is an opponent who is working against you. A very good example is chess. Now, in a state model based or a state-based model, solutions are procedural. They specify step-by-step instructions and how to go from A again to B. In some applications, the order in which things are done isn't important. So it's not in sequential order. So for example, would be Sudoku, where the goal is to put digits in the blank squares to satisfy some constraints. All that matter is the final configuration of numbers. You can fill them in any order. We also have variable-based model allow you to again declare your what you want. It's like again higher level languages rather than micro manage how you want the solution to be. Now, constraint satisfaction problems are again variable-based model where we only have hard constraints. For example, in scheduling, one person can't be in two places at the same time. We should also see the Bayesian networks, which also are variable-based models where variables are random variables, which are dependent on each other. So for example, the true location of an airplane height and its radar reading are related as are the location, let's say HT, and the location at the last step, which would be HT minus 1. Then the last topic is logic. And this concludes our tour of the topics. So to summarize, we will discuss models going from refresh to state-based models to variable-based models to logic. And also we're going to focus more on the machine learning algorithms. And also for each, we would instantiate the modeling, inference, and learning paradigm. So again, see you in the next lectures. These slides came from stanford.edu online.